Hi, welcome back. In this lecture I want to introduce a special kind of complex matrices called Hermitian matrices. We're going to find Hermitian matrices all over the place when doing quantum computing, and therefore it's important that I provide you a more formal definition so you could understand the properties. But let's start with some few concepts that we need in order to explain the Hermitian matrix. The first concept that I'm sure you already encounter in your education is the concept of a transpose of a matrix that is typically denoted with a T on the top right of the matrix. We applied our transpose operation. So what is the transpose? Well, transpose is just an interchange of the rows with the column. So for instance, here we have our matrix A that has A, C, B, B, A, C. And what we're doing in this transposition is to take the first row that goes as the first column. The second row is interchange with the second column. And then finally, we have the third row that becomes the third column. So it's just a simple operation. So given any matrix A, we can just interchange the row with the columns and find the transpose. So this is kind of classical, nothing to do with the complex number yet, nothing to do with the quantum computing. Something more related to quantum computing, and particularly to complex matrices, is the conjugate. So what is the conjugate of a matrix? So we saw what was the conjugate of a complex number. It's the very same things for complex matrices. So basically, we just conjugate each element of our complex matrix. So in this case, we have this matrix here, and we know that the conjugation is basically change the sign of the complex matrix, and we do this operation all over the elements. So the first element is 1, doesn't have any imaginary number, so it remains the same. The second element here on the top right has plus I. We apply to this element a conjugation, and so in this case it's going to become minus I. We take this element here, we have minus I, and we flip the sign, so we're going to be plus I. This element here is I, we flip the sign. 5 doesn't have imaginary part, so we don't do an operation. Last but not least, we have this element, we basically flip this sign here. So we can do an operation on complex matrices that is called the adjoint. So the transpose operation, the conjugate operation, can be actually combined and form the so-called adjoint operation. So this operation forms a so-called adjoint matrix or adjugate matrix, or also the dagger matrix or operation. The adjoint is denoted in a different way. Sometimes you see this symbol here that is called the dagger. That is the dagger operation on A is nothing else than taking the conjugate operation and then the transpose, or vice versa. We can take the transpose and then take the conjugate operation. So in this forms here you can see basically we do transpose operation and then we can take the adjoint. So let's see here an example of the matrix A. We could do both, either first the transpose and then the conjugate, or the conjugate and then transpose. In these slides we do first the transpose, and see we basically interchange the rows with the column, and then we take the conjugate of this, and this is going to basically flip the sign on the imaginary part. So in summary, the joint operation combines a transpose operation with a conjugate operation. The order doesn't matter since they give the same results. It's important also to talk about symmetric matrices, because we see that Hermitian matrices are just an extension in the complex realm of the symmetric matrices. So what is a symmetric matrix? A symmetric matrix is nothing else than a matrix whose transpose is equal to the matrix itself. So A transpose is equal to A. So if this holds, then our matrix is symmetric. We have an example on these slides of a symmetric matrix. You see, for instance, the first row is equal to the first column, the second row is equal to the second column here, and the third row is equal to the column. But this is the very same matrix, therefore the matrix is symmetric. As I told you, Hermitian matrices are an extension of symmetric and a generalization of it. So we can generalize the notion from real number to the complex number and introduce the concepts of conjugate plus symmetric. So if we can do a conjugate plus symmetric, then this matrix is called Hermitian, and we can express like this one. If a matrix is Hermitian, so is symmetric and also conjugate, then the operator that represents is called self-adjoint. So let's see an example, for instance, of Hermitian matrix. So this matrix is T matrix and also conjugate. So you see, for instance, we have the first row here is equal to the first column here, except that we're taking the conjugate, so the plus here become minus, and then here the minus become plus. The second row becomes the second column, changing the sign here, and finally the third row is equal to the conjugate of the third column. So you see change of here of the sign. We can note is that the Hermitian matrix must have a real number along the diagonal matrix. This need to be equal to its own conjugate, so that means that there is no imaginary part. So from the definition, we can say that along the diagonal Hermitian matrix must be real. In addition, the whole notion of a symmetric matrix is a special case of Hermitian that is limited to matrices with only real entries. So any symmetric matrix with real values is also Hermitian, right? Because we don't have the conjugate part. So why we introduce Hermitian matrices? Well, the reason for that this is extremely important for quantum computing. It turns out that in quantum mechanics, associated with every physical observable, like position, momentum of a quantum system, there is a corresponding Hermitian matrix. So we can express always every physical observable using an Hermitian matrix. So measurement of that observables always lead to the state that is represented by one of the eigenvectors of the associated Hermitian matrix. So in summary, we basically deal with the special class of complex matrices called Hermitian matrices. These are a generalization of symmetric matrices, but using complex value. So not only are symmetric, but also has its own equal to its own conjugate. So this is the last slide of this lecture, and talk to you soon.